Big O notation, the standard we use to classify the speed of algorithms. When you're working on large projects with a sizable user base, it's important that the algorithms you use are as efficient as possible to make sure that the software operates smoothly and without delay. We can't just use a timer to measure the speed of algorithms because the speed is relative to the input. The larger the input, the slower the algorithm is going to be, and there are an infinite number of input sizes we would need to test out. We refer to how the efficiency of an algorithm increases relative to the input size as the growth rate, and we use Big O notation to describe that growth rate. Big O notation doesn't look at the exact running times of algorithms. Instead, it looks at the worst case scenario so that we can see how an algorithm would perform in the most demanding of situations. There are other notations which are used to classify best and average case running times, and I'll cover those in another video. The most common running times, from slowest to fastest growth, are constant growth, logarithmic growth, linear growth, polynomial growth, exponential growth, and factorial growth. Algorithms with constant growth never actually grow, and those with factorial growth become unfeasible very quickly as they can only handle small inputs efficiently. But how can we work out what the Big O notation for our algorithm would be? Well, to do this, there are two important things to note. First, when adding terms in a function equation, you can work out the growth rate of each individual term. Then, the growth rate for the whole function would be equal to the fastest growth rate. For example, if we had the function f of x equals 1 plus x plus factorial x, the fastest growth rate would be of the term x factorial. So we can say that the overall function has factorial growth. Second, when multiplying terms, you multiply their growth rates. If you had n multiplied by log n, the running times of each of these individually would be O of n and O of log n respectively. Therefore, the growth rate of the function f of n equals n times log of n would be O of n log n. Let's work through an example together. Say we had the function f of x equals 3n plus log n plus 2n cubed. Before we go through the solution, see if you can work out the answer for yourself. If you determined the running time was O of n cubed, you got it right. Let's see how we could get to this answer. Firstly, we notice that there are three terms being added together. So in order to find the overall running time, we can find the growth rate of each individual term. The maximum growth rate from the individual terms will be the function's overall growth rate. For 3n, we know 3 has constant growth rate and n has a linear growth rate. So these multiply together to give us O of n. Log n has a growth rate of O of log n, and 2n cubed has a growth rate of O of n cubed. Out of these, O of n cubed has the fastest growth rate, and so we can say that the rate of growth for the entire function is O of n cubed. When deducing the growth rates of algorithms by looking at their code, we can have a look at each segment of the algorithm and work out its running time. The largest growth rate will be the growth rate of the entire algorithm. There are two things to know which will make this easier. You can add the running times of consecutive loops and multiply the running times of embedded loops. There are many different ways to sort an array of numbers, but they're far from equal. First up, linear sort. If we have a look at this algorithm, the first thing that we can see is that on line 2, we're assigning a variable. Typically, variable assignment is done in constant time. Returning a value also is done in constant time. A quick thing to note is that if the operation you're doing does not depend on any sort of input size, then the running time is going to be constant. For example, looking back at line 2, no matter what we're assigning to max value, the input size is always going to be the same, whether you're assigning it a 1-digit value or a 10-digit value. However, if we look at this for loop, it does depend on input size because you could have an array of length 1 or an array of length 10,000. And it's a lot slower to iterate through a for loop 10,000 times than it is to iterate through a for loop once. Therefore, the running time of this for loop does depend on input size, and since it looks through each value of the array once, we can say that this for loop has a linear running time. If we look inside the for loop, we can see that we're checking if the number is greater than the max value, which is done in constant time, and then within the if statement, we're assigning a variable, which is done in constant time. Therefore, throughout this entire algorithm, every line line is done in constant time, apart from the for loop, which is done in linear time. And since this has the fastest rate of growth, we can say that the overall running time for linear sort is linear time, so O of n. Next, let's have a look at quadratic sort. As we can see on line 3, we're assigning a variable, so this line is done in constant time. This if statement also doesn't depend on any sort of input size, so it's done in constant time as well. Checking if one value of an array is greater than another value of array doesn't depend on the size of the array, so this is done in constant time, and so is this variable assignment on line 6. The only things we have left to look at are this for loop and this for loop. Both of these for loops depend on the size of the array. Whatever the array size, that's the number of times we're going to iterate through each of the for loops. However, as I mentioned earlier, if you got an embedded for loop, then you multiply the running times. This for loop would have a running time of O of n, and this for loop would also have a running time of O of n. However, since it's embedded in another for loop, the overall running times of these for loops is O of n times n, so O of n squared. And therefore, since the rest of the operations within the quadratic sort algorithm were done in constant time, we can say that the overall growth rate of this quadratic sort has quadratic growth. Let's have a look at how the running times of these algorithms actually compare. As we've seen, linear sort has linear growth and quadratic sort has quadratic growth, and so we would expect quadratic sort to be slower than linear sort. But is this actually the case? Let's create an array of random numbers of length 1000. We can then import the timeit module to time how long these functions actually take to run. Here I've implemented some code that will run the quadratic sort and linear sort algorithms 100 times each and work out the average amount of times it takes to run each. Let's run this in the terminal and compare running times. As you can see here, the linear sort ran, on average, in 0.00118 seconds, whereas quadratic sort ran in about 0.016 seconds, which is a lot slower than linear sort. And so we can see that the running times works out in big O notation are reliable, even though these running times are very small. And we couldn't actually feel that quadratic sort was a lot slower than linear sort on scales much larger than this, where the array size is a lot greater than 1000. The running time of the function we chose to use would be a lot more impactful, and so on larger scales we would opt for linear sort over quadratic sort, since it's a lot more efficient. If you have any questions about big O notation or didn't understand something I mentioned in this video, drop it in the comments below and I'll get back to you as soon as possible. If you like this video and want to learn more about computer science, then check out this video on the screen and don't forget to subscribe. Have a great day and I'll see you in the next one.